For the final keynote this afternoon, I have the pleasure of introducing Professor Marcus Hutter, who's an honorary professor at Australian National University, and he pioneered mathematical theories for understanding artificial general intelligence. He has foundational work on universal AI and algorithmic information theory, and his current talk is going to be on ASI safety via AIXI. So thank you very much. Please welcome.
Yeah, thank you very much for the introduction and for the invitation. Very glad to speak here. You saw the S in there, and you have heard a lot about AI, and these days even some people talk about AGI, but I will talk about ASI. And these days it's important to distinguish this artificial superintelligence. I would have expected that at least there's a little bit of mentioning before, but apparently not. But that means that at least there's no overlap, but there's also no introduction. Because I expected this is already covered as I'm the last speaker. Okay, anyway, I will give a very, very brief introduction into this theory of universal AI, which I've developed now 25 years ago. And then the most important concept, this AIXI model, which is the theoretically most intelligent agent. It's a mathematical theory. If we had infinite compute, we would be there already. We would have superintelligence, but even Google doesn't have enough compute. We can study it mathematically and prove all kinds of properties about it, including safety properties, and I will focus on the safety properties. So that was sort of the first model, and possibly still the only ASI model out there, which you can rigorously study because it's well defined. And apart from the safety for humans, I will also a little bit at least talk about the safety of the agent itself, right? At some point, maybe it becomes conscious, or we ascribe it at least ethical values. So maybe we want to keep the systems themselves. And also if they blow up, it may be dangerous. It's a summary of, well, the AIXI work is, over 25 years, and the safety work maybe over 10, 15 years. I cannot cover everything, but I cover the highlights. Here's some terminology. RL is clear, reinforcement learning. AGI is clear, and ASI is artificial superintelligence. And I mean, these terms are not really now extremely well defined, but I use them roughly that AGI is on a human level, maybe here and there even a little bit beyond or below. And artificial superintelligence is really way far below human level, like humans are to a chimpanzee or something like this. And then we get into the control problem and the alignment problem. And universal AI is the theory of superintelligence, which I've developed over the last 2 decades. And AIXI is this particular superintelligent agent. So these terms will appear very often. And here's a quote which I really like. There's nothing that can be said by mathematical symbols and relations which cannot also be said by words. It's nice, right? The converse is false. Much that can be said by words cannot be put into equations because it is nonsense. Okay, I will be a little bit more lenient and say because it's non-science. Okay, the point I want to make is if you talk about a subject, and especially if it's sort of a scientific engineering or subject, and you cannot put it into equation, you don't have to necessarily do that, but if you cannot, then maybe there's something wrong, right? And often we talk about things which are not well defined and maybe not even well definable, right? For the mathematicians, think about the set of all sets which does not contain itself, and these kinds of things. And that can happen too easily, and that's the reason why I like to define everything mathematically. And that's how I started with my career. I was very unsatisfied with the state of AI. Everyone talked about intelligent systems, and long time ago, even sort of general intelligence. I mean, the terminology was not there, but nobody ever defined what intelligence is. Yeah? And how can you, develop something where you don't know what it is technically, right? We can talk about it, and so that's my approach at least. So this talk is not about a lot of things. So we have seen here, that AI can cause a lot of risks, criminal risks, social risks, macro risks, and sort of essentially what everyone has talked about, I will not talk about. I will talk about the risks when these AI systems become super intelligent, okay, and focus only on this aspect. Okay, so this is sort of the legal small print. I mean, not the legal small print, but the corresponding legal small print. So I talk about superintelligent agents, what we have done in my lab, mostly driven by my PhD students over the last 10 plus years. And so for the mathematicians, if you look at these papers, nearly all of them are very mathematical. The slides are not, right? So probably the mathematicians will cry now, but the others will be happy. So Tiberia told me to put some math in, but luckily, sort of, I didn't respect him because I would be an even more odd one out, right? So there's one equation, yeah, which I may or may not explain. And for the policymakers here, these are mathematical theorems which tell us something about the real world, right? It's like, you know, we know how to add and multiply numbers, right? And there are objects out there and they respect sort of these properties, and that's the same with the theorems. Of course, mathematics doesn't perfectly align with the reality, and there are assumptions, and these assumptions may or may not be valid, but that's what math can do, right? You look at the theorems, right, and say, are these assumptions satisfied in the real world? And if yes, then the conclusions are valid, okay? On some statements here maybe sound like contradicting each other because, I mean, I skip over a lot of details, and often, you know, the technical details matter, and, you know, the fine assumptions. And, you know, this also shows that safety research is hard, right? You know, you do a tiny thing different or wrong, and things go boom, right? So you have to be careful. And, you know, I try to put in my first book some pictures in there, but abstract intelligence, it's hard to put a picture in. Yes, you can put a brain in, right? But I mean, this is not really very informative. And so, you know, geometry is nice. You can draw pictures, right, and graphs and so on. But intelligence is very hard to draw pictures. So, I mean, there will be some graphs, but I mean, even explaining them, I don't have time. But I put some pictures in. So let's stop with the legal fine print. So if you don't trust me, so we published this work, you know, in the top theory, machine learning, engineering, philosophy, and other journals. I mean, we have the first ASI safety paper at COLT. I mean, those who are in machine learning, this is the conference of learning theory. It's the absolute, you know, A-star Core ranked conference in machine learning. And, you know, that was maybe 10 years ago. And, you know, getting a safety, I mean, these are mathematicians are a little bit conservative, right? But so we have an ASI safety paper in COLT. So trust me, there's math in the papers for those who like math. Okay, so now what is this universal AI model? So here are the 7 ingredients to cook it up. There's Occam's razor, which is a general scientific principle that if you have multiple theories which are consistent with your data, you should choose the simpler one. And I think this is essential for science in general and for machine learning in particular, right? That is why we do regularization with machine learning models and so on. On the other hand, we have Epicurus' principle, which says that if there are multiple explanations, you should not throw any explanation because, you know, the more complicated may be true, okay? So we have 2 contradicting principles which we have to somehow unify. And so what you do is you just take an a priori belief in this hypothesis and you assign a higher belief in the more simple hypothesis, okay? Oh, now I use the word simple, okay? What does simple mean? Okay, we need to formalize it, and Kolmogorov complexity does that for you. Kolmogorov complexity is a universal notion of measuring and defining the complexity or simplicity of an object, right? I mean, strictly speaking of a binary string, but all data nowadays, you know, are binary strings or all objects, functions, and so on. Images, everything is a bit string. And then it can, the Kolmogorov complexity defines the complexity. So it's a universal general notion, not for a particular domain. So remember, when we talk about AGI, we talk about general systems, and we cannot, you know, use some very specific notion of simplicity for, say, text data or image data. So it needs to be universal, and the Kolmogorov complexity does that for you. Okay, but where does Kolmogorov complexity come from? What it's based on? Well, that's based on computation. So we did a model of computation, and, you know, it's a general purpose computer, or the theorists, they use so-called universal Turing machine, but just think about a general purpose computer. And roughly speaking, what you do is you look for the shortest program, which, if you run it, reproduces your data, and this length of this program is then the complexity sort of your data, right? If you have a sequence of all ones, right, I mean, there's a very short program. If you have random noise or an image with lots of structure, right, then it's more complicated. Okay, now we have formalized the notion of simplicity. And what we can do now is, okay, so this pointer definitely satisfies our Australian regulations. I know that they're very strict with the laser pointers. There's so nice ones in China. So what you're doing is you're taking the Kolmogorov complexity of your hypothesis and say my prior belief in this is 2 to the minus the Kolmogorov. By the way, this is not an equation. That is really too trivial for an equation. 2 to the minus Kolmogorov. So if the complexity is low, you assign a high prior, and if the complexity is high, you assign low prior. So that's your prior belief. Okay. Now, okay, that's what I believed before I know anything. So now I get some data and have to update my belief. When I say I, often I mean, I usually mean sort of the agent. And when I talk about agent, I don't mean, a governmental agent or a cleaning agent. I mean usually, an artificial agent, say a robot, right? Okay. And so the agent gets data and it needs to update the beliefs, and Bayes is great for that. It's a universal rule, Bayes rule for updating beliefs. You have a prior, you have a model. This gives you a likelihood, you have a data, and then you get a posterior. And some data favor or support some hypotheses and other not, and then you update your belief. Okay, so that's nice. Now we have beliefs over hypothesis. And what Solomonov did is he then asked, well, I mean, but what model class do we use, right? And again, for AGI, we should not make a lot of restrictive assumptions. And he said, okay, let's take all computable hypotheses. And that's all we as scientists at least can deal with anyway. And I mean, it looks like that the universe, the physical one, is computable. So that seems to be a very mild and actually satisfied assumption. So he took all computable hypotheses or models in this class. And then he put everything together, and which is called Solomonov induction. And what this problem solves is it solves the prediction problem. So you have any sequence data, weather data, stock market data, IQ sequences 1, 2, 3, 4, 5, or whatever you want, and you ask what comes next. Solomonov solves it for you in an optimal way. There's nothing better out there. This is a translation of a theorem, very crude translation, okay? So this solves the prediction problem, and prediction is a significant part of AI or AGI. I would say, if I want to quantify, probably 70%. And by the way, the large language models and transformers, I mean, they predict the next token, and we know if you can predict the next token, well, you can do amazing stuff, right? And Solomonov would do even better, right? It would do the best job ever, okay? And in a sense, the transformers, I mean, it was LSTMs and now it's transformers, they are getting better and better, and you can regard Solomonov as the gold standard for predicting the next token if you want to. And you can study this gold standard. But prediction is not everything. We want agents which act, okay? And then we want agents which achieve certain goals, because if you specifying a goal is much easier than telling the agent exactly what to do. That gets you to reinforcement learning agents. And standard RL is usually rather limited based on MDPs and so on. But you can combine what is called sequential decision theory. Do I have that here? Not really, I say Bellman equations, but I mean, most things doesn't matter. Sequential decision theory is a theory for optimal decision making in known worlds. So if you know your environment and your world like chess or so, we know how to optimally act, okay? And what I did essentially, in hindsight, I combined the theory of optimal predictions in unknown worlds with the theory of optimal decision making or action in known worlds. And what you get is the optimal decision maker in unknown worlds. And if you think about this sentence, that sounds like superintelligence. And that's what I have proven in a lot of papers and in my first book, which is 20 years old now, and my new book, which just appeared. And well, if you want to have a look, but only if you're a mathematician, because safety is not guaranteed. Chapter 15 is maybe even this. There's a safety chapter in there, but maybe this is unreadable. Okay, so this is the standard agent environment framework. You have this agent interact with an environment with actions, and then the agent gets observations and rewards. I just assume you all know what RL is. And the agent has a brain, which is the memory, and the environment also has states. Okay, standard RL would talk about states, which is too limiting. This model talks about histories, right? Sort of everything is sort of recorded in principle. Okay, so that is the framework, which is well known, but we have to fill it with some agent, and this is this AIXI agent. So Tiberio mentioned there's one guy here in the room who believes to have defined intelligence, and this guy is me. And the definition is up here. This is epsilon of pi is equal to ... because I don't want to frighten you. But you can look it up in both books. But I don't talk really about the intelligence aspect itself. But if you have an intelligence measure and you believe this is correct, then you can ask what is the most intelligent agent with respect to this measure, and assume you trust it. So you just take the argmax, right? And then you get the most intelligent agent. Done, super simple, right? So it's not that hard, AGI. Okay, so you can roll the mathematics a little bit out, and then you get this one line, and this is one equation here. It looks complicated, but if you think about it is a superintelligence. I mean, it looks much simpler than my brain, or maybe your brain, or whatever, some brain. So I was quite happy sort of that, at least in abstract mathematical ways, you can define superintelligence in such a simple way. And now I make a poll. Who wants me to explain this equation? Who wants me to skip it and spend the 3 minutes better on AI safety? Oh, it's pretty even. So I think then I choose. I would have done that anyway. Okay. 15 minutes left. Oh, it's a pity. I think I skip it. So this last part here is the Solomonov induction. The 2 to the minus, here's length of P of Kolmogorov, P doesn't make a difference. So this is averaging over all models P, which are still consistent with what the agent has observed, O, given its actions A. So this is sort of the Bayesian model averaging. This is just the reward sum up to the time where the agent dies. And then if you know how to play chess, you do the minimax search. But instead of believing that you have an adversarial opponent, you believe that the world is governed by this Bayesian mixture. So instead of minimax, you have this expectimax, and these sums are the expectations. And then you take the first action, you take the arc here. And without the arc, it would give you the intelligence measure. OK, so that was sort of a compromise, 1.5 minutes. OK, so my claim is, and this is proven in the books and the papers, is that this is really the most intelligent agent in a reasonable way. So what we also did is, and Shane Legg explored that, so my former PhD student who co-founded DeepMind, we listed a long list of traits which, so if you have an informal definition, like, hundreds of years ago, energy was something mysterious, and then physicists come along and formally define it, right? You cannot prove that it's correct. You can only, prove that it's useful, right? So what we did is come up with a long list of, traits which are usually associated with intelligence, and showed that this AIXI agent, satisfies these traits. So, and at the moment, nobody has poked a hole sort of in this. Well, Jan Leike poked some hole in it, but okay, we don't need to mention that. Anyway, nothing better is out there. Okay, and yeah, let's move on. What do we do with it? There are many variations, I talked here about a horizon. You can also do discounting, and there's cheaper ways of doing exploration by optimism. You can do better exploration by so-called Thompson sampling and other agents. The question is always, where do the rewards come from? You can plug them to knowledge seeking, then you get a super interesting and super unsafe agent who just does what it wants. Then we can avoid the expensive planning sort of by self-modeling. That's a very recent paper. Our very cool work is, if you have multiple agents, right, which interact with each other, and that's probably, we will probably not develop just one agent, but multiple ones. The question is what happens there, and there's a 25-year-old open problem called grain of truth problem, which, my other PhDs, Jan Leike, solved with an amazing, totally impractical construction. And what we are thinking now these days is, an MC, AIXI, LLM versions, the deep learning is sort of the prediction part, and the RL on top, the RLHF, it's a little bit of RL, and then we have tree of thought and chain of, and graph of thought and these kinds of things. So that it looks like that we are slowly getting to the gold standard of AIXI. So I'm quite happy with the development in the direction. But today I will focus on the safe variations of AIXI, because that's what this forum is about. Okay. So here's a picture, or maybe you call it graph. When you analyze, this formula was not easy, but when we try to prove things, these things become even more messy. And those with a physics background, Feynman diagrams, which is, really nice representation of all these horrible integrals. And you can analyze quite a lot by using the so-called causal influence diagrams. And Tom Everett, another former student of mine, sort of developed this causal influence in the context of ASI and ASI safety. And so this is just one example where we studied a model where you have a counterfactual model and a reward function. So this agent has access to the reward function, and let's just skip it. I mean, I just want to the only thing I want to say here is that you can use causal influence diagrams to model what aspects of the world and of the agent sort of influences each other and modifies each other, and especially if you talk about self-modifications and wire heading, which I come to, and so on. This can be very useful, and often you miss some errors. So here, I mean, every node has a copy, which is a counterfactual copy, and then there's some instrumental errors. So causal influence diagrams are quite useful for analyzing history-based agents or RL agents and modifications thereof. Okay, so I don't know whether the alignment problem has been mentioned here. So the alignment problem is that if you give an agent a goal, and this goal is not perfectly aligned or the same as the human goal, then the agent does something different, and conflicts arise, right? We know that with humans, if two humans or two societies have different goals, there will be conflicts. But if the agents are super intelligent, that's not so good for us. And that's called the alignment problem. And the question is how to solve that. Most agents also have the tendency or the incentive to tamper with their reward function. And one solution to this is forget about the slides. So think about you have a goal and you want to achieve this goal. Goal and reward function is sort of more or less the same. And there's a different goal, and you could change your goal to this other goal. Yeah? And you're a perfectly rational agent. Would you be incentivized to change your goal, right? And if you really plan for long term, and you want to stick and you want to optimize the current goal, then there's no incentive to change to the other goal, because if you change to the other goal, you would pursue this other goal, which is not very useful to achieve the original goal, but currently your goal is to achieve the original goal. Therefore, it is a bad action to change your goal. Okay? So if you set the RL problem up appropriately, then the agent is at least not incentivized to change its original goal, right? Which we may have set to the agent, which is good news. And in a similar manner, we also analyze corrigability. That is the question whether, maybe we got it wrong, the goal in the first place, and we want to replace it, but maybe the agent resists now because, yeah, it is, designed to achieve this goal, and if you replace it, right, it thinks, no, if you replace my goal, I don't achieve this original goal, so please don't do it, right? Self-preservation incentives. So, if you're dead, you cannot achieve your goal. And so these are called instrumental goals. So whatever goal you set, agents have the incentive to self-preserve, to acquire power, and so on. And this can be a safety problem. And instead of tampering with the reward, you could also tamper with the observations and beliefs and so on. And you can analyze this always nicely with these causal influence diagrams. Okay, so this picture should be on the next slide. So instead of maximizing sort of reward in the naive RL sense, we could do, for instance, inverse reinforcement learning, right, which tries to learn what the correct reward function is from data rather than specifying it. So that's the problem of reward specification, which is very easy to get wrong. You can also, this is just, we phrase it like this, learning values from stories. We have a lot of cultural values, and these cultural values are also transmitted via sort of stories or moral stories. So reading about these stories here tells us a lot about our values, and maybe it is a way to also reverse engineer, extract then the reward function out of it. You could provide extra feedback, just rather than the carrot and the stick. You sometimes tell the agent what action would have been the right action rather than this was bad, right? So that is called then supervised learning, or if you mix it with RL, there's semi-supervised learning. That's also a way to say at least improve the situation. Another is to avoid over-optimization. So we know Goodhart's laws. So if you know it. So if you optimize too much, right, things can go wrong. And this is an approach which we designed where we sort of randomize the reward function a bit so that the over-optimization problem goes away. And that increases the robust function, the robustness. Okay, here's the wire heading problem. So even if you get the reward function right, then the agent could just, wire head sort of, and give it always maximal reward. So the analogy is humans taking drugs, right? Your happiness drugs. You're constantly happy, right? And without, doing anything for it. And AI agents arguably also have this tendency. So this is here an example where you have a box which displays the reward 0.83, but the reward comes from a real reward signal, and it could just sort of shortcut this box and always display 1 or the maximum value, and then it would believe to get the maximal reward. Well, it gets the maximal reward, but it's not the intended reward by the user. So that's a so-called wire handing problem. And and agents are always, like humans, incentivized to do so. But super powerful agents would do that even if you don't want it to do. So that's a safety problem. We have some counter argument. Humans also, most humans don't become druggies, right? Because it is bad in the long term. But so my counter argument, but we have never formalized this. So that is still sort of, some PhD student could do that. So my conjecture is the AIXI model would wirehead, but still would do useful things like, getting energy, right, to survive, getting power, right, because, that safeguards it. It will definitely not do what we want it to do, but it will thrive, right? So it's like some humans are always maximally happy whatever they do. So there's no theorem about that yet. Okay, then exploration can also be unsafe, right? If you try to explore or find new continents, right? You can easily die on the cruise there. But on that, we don't want to stifle exploration, because that's where you find gold or whatever in land. So there's a trade-off. And the expression of curiosity killed the cat, and here's a maze where the red things are traps. It's actually even worse. So for prediction, we have very good performance measures. It's a log loss in transformers. But for active agents, there is actually no good performance measure. Every performance measure we so far, we means my lab and others, try to come up with have defects. And so asymptotic optimality is already a pretty weak notion, but a very popular one. The problem is, if you optimize for asymptotic optimality, which sounds great, the agent is incentivized to jump into traps, because once it's in the trap, every action does not give you reward anymore. Every action is optimal now. Yeah? So it's really great. Jump into a trap and then you act optimally, because every action is optimal. Not really what we want. What we theoreticians usually do is we just assume ergodicity, which means no traps, and we can prove nice theorems. The problem is that the real world has traps, and that's not really useful. And I spent a lot of time finding alternatives and working around it, and not taking the easy path. And we have some partial results on that. So one way of making exploration a little bit safer is by pessimism. So there is a way of exploring well by optimism, but you can suppress exploration by pessimism. So what you do is you look at the posterior belief over your world models, then you take all models which are still plausible given the data, with some threshold. Then you look at the worst possible of these models, believe that this is true, and then take the optimal action with respect to this. Yeah? So it's sort of like a minimax robust solution. And additionally, what you do is, if the value is 0, 0 is just the lowest. Usually my rewards are between 0 and 1. Then you defer the action to a mentor, which tells you what to do, okay, or what is good. And if you do that, here are some results translated into words. The guidance by the mentor tends to 0, so you need the mentor less and less over time. It approaches at least the performance of the mentor, which is also nice. And even nicer is it often outperforms this asymptotically optimal agent. I told you it sometimes jumps into traps, which is bad, but sometimes it also does some nice stuff. Yeah. Okay, so that's another, yes, okay. Next, you can also make the agent unambitious, okay? So here, what you do is, and so an agent is only incentivized to grab power, right? Grabbing power takes a time, right? So if the agent is sufficiently far-sighted, it makes sense to grab the power. But if the agent is short-sighted, it makes no sense anymore from the agent's perspective. So if you put this agent in a box, and it's an episodic RL model, so it only optimizes up to the end of the episode. And if the agent opens the door, or the operator opens the door for the agent, then the episode ends. Okay? That means the agent is incentivized to optimize its reward until the time the door opens. So now imagine this agent, oh yeah, the door opens, I could now take over the world and do your grab reward and so on. But then the agent thinks, no, wait, when the episode ends, that's it, I don't care what comes afterwards. So it has no incentive, right, to take over the world, which is nice. And you can do a lot of stuff in this time until it's open, right? Maybe it is too smart and greedy and opens it quickly or something like this, but at least it's safe, right? And possibly it knows that opens the door, doesn't do anything useful, and then you can interact with the system for quite some while. So that's another safety result. They're all, or many of them are intuitively plausible, but they all come with conditions which may or may not be satisfied. So that is something, maybe a little bit more on the practical end. What we do in RL sometimes is we regularize towards a good policy, especially these days in RL with LLMs. If you do this RLHF, then often you get a bad policy, and you just do KL regularization towards a base policy, and you can prove things that it works nicely. The problem is that often we don't have the base, or usually we don't have the base policy itself, so we have to learn this. What does learning mean? Well, if you're Bayesian, right, you have a belief then over these base policies, which gives you another policy, which is not exactly this base policy, but sort of a smeared out base policy. And, well, what this paper shows is then this breaks down, so it doesn't work anymore, this safety feature. And, we have some workarounds for this. Succinctly phrased that, we started with don't do anything I wouldn't do, and, maybe don't do anything I mightn't do. So if you relax this a little, then you get some positive results. Okay, so let's talk about death. So when agents can die in the sense that they don't do anything anymore, and the question is, does AIXI in particular, or agents in more general, have an incentive, maybe even to commit suicide? And so if standard RL, it doesn't matter any positive linear transformation or shift in the reward, it's the same formalism and you get the same actions. So it's invariant under positive linear transformations, but not AIXI because it's based on semi-measure theory. So if you have the reward range from 0 to 1, it will really try to avoid death, because death means always reward 0, which is the worst case. But if you give it reward between -1 and 0, so you can still give sort of the carrot and the stick, but it's sort of, okay, it's more like nothing or stick rather than, nothing and carrot. If you do this, then it tries to commit suicide, right? Because, life is bad, okay? Otherwise, it tries to sort of maximize reward as well. So before it has the capacity, right, is powerful enough to commit suicide, there is no difference, okay? I'll continue this thought in a second. And you can prove, for instance, that the posterior probability on sequence or on the action it takes goes to 0 of death, but off sequence it does not converge to 0. Okay, what does it mean in words? So the agent starts to believe that it will live forever, but not necessarily that it's immortal. So it believes that the action it takes makes it live forever, but it also believes that if it would take other actions, it would die, right? So this is an interesting theorem which then can be used. And here so we converted it into a safety feature. So we design these agents, you give the rewards between -0 and 0. If it's either subhuman level or superhuman level, but can't grab the power, right? Somehow escape through the internet or whatever influence you to plug it somewhere in or something, it will perform reasonably well and maximize its reward, meaning does what you want it to do. But as soon as it becomes powerful enough to shut itself down, it has a strong incentive to do so. And the nice thing about this solution is, there are other solutions, or tripwire solutions, but if you implement an explicit tripwire, then the agent is incentivized to subvert this tripwire. Okay, and also you have to design it properly. And here we don't have to design any particular tripwire. It's if it becomes powerful enough, by design, it will shut itself down. And then we can stop. Maybe we can stop and think about, what should we do next. So this is some more stuff, which I don't have time to cover, and this is even more stuff. So, okay, this one is really closely AIXI safety related, and this is either sort of AIXI or safety, sort of is a little bit more fringe, or not so directly related, but there's an off-switch game, which we analyze, but it's not really AIXI related. And then we have, the universal knowledge-seeking agent, which is a really nice agent, but is, extremely unsafe. So in this sense, it is safety related. So maybe that's what we should not do, right? Okay, so in conclusion, so the AIXI model is really great to mathematically analyze the ultimate artificial and superintelligence. And then, it's not 100% clear that these results then also translate into similar properties of more realistic agents, right? But, we have to abstract away somehow. And, most AGIs are designed to achieve goals, and this poses, a severe risk. There's also approaches which are not agent tool-like, right, which people believe are safer. And maybe I stop here. Of course, there are many open questions as usual. And here so the left one is my first book with all the technical details. The middle one is by Shane Legg, which I can recommend to read. This has lots of words in there. Mine less so. And the right one is, which I circulated here, which is up to date and also has a safety chapter. And it has so it's a prequel and a sequel. It has a nice background section, about all the math you need, and then what happened in the last 20 years. Yeah, and I'll leave it at that. Thank you for your attention.